Hello world, this is Craig. Just got these boards in the mail and populated this memory expansion board. This is one that I mentioned in an earlier video when I was looking at the prototype for it, but this is version 1 and I've got it populated and I'm undergoing testing now. It looks pretty good. So far I haven't found very much that I really don't like about the board. But I wanted to show you about some of the features on this board and how it's used and basically what this board does. So you can see that this kind of extends from, the screwdriver up here at the top to my fingertip down here at the bottom. That everything between that is for that particular channel. Then all the stuff that's out here on the left-hand side and across the bottom is for decoding this entire board. So let's look at what we do for each channel. Now, a slot can have either 2732, 64, 128, or 256 EPROM. It can have a 6264 RAM, and it also should be able to have a double EPROM, like a 2864 or 28256, although I haven't written the software yet to test those. But basically what we have to do is put the chip in, and we have to set 3 jumpers for that particular chip. And you can see there's a jumper up here at the top, there's one here just below the device, and then there's one down here at the bottom. And those 3 have to be set for a particular chip. And there's a little map on the back of the board, the silk screen, that shows you that, for any particular jumper, whether it's open or it goes to the right or to the left or up or down or however that jumper is configured for that particular device. Then there's 7 more jumpers in here, this little array of 3 times 7, and this is to determine the address of that channel. Now each of these 4 channels is completely independent as far as their addresses go. So let's look at how this address is actually decoded. Of these 7, 4 of them are the top 4 bits of the address on the bus, so A15, 14, 13, and 12. What we do is when we want to claim an address space for a particular chip, we put in jumpers to mask what address we're interested in. And we can either say that we want that address to be 0, we want that address to be 1, or we don't care what that address is. So if we look at this 2732, for example, we're saying that we want address 15 to be 1, so the jumper's not there. This jumper is in the 0 position, and then this is in a 1, and that's in a 1 position. Basically, if we don't put a jumper in, that address line indicates that it's going to be a 1. Now, in this device, we have the jumper on the right-hand side, and if it's in the right-hand side, that's a don't care. We don't care what that address is. And the reason we have to use that in some devices is if that device has an address space that this address line is decoded inside that chip, then when it comes to decoding that chip and selecting that chip, we don't care what that address line is, because if that address line is 0 or if that address line is 1, either one of those would select this chip. So for example, I'm putting together a little configuration cheat sheet here to remind me of how I've populated this thing. And so we can see if we got like a 2732, I put in here that we're going to set up our mask, and we want our mask to be 1011, and that's what I showed you earlier in the way that those jumpers were set. But if we're using that for a 2764, then our mask is a 110 don't care, because we don't care what this bit is, because this bit will either be a 0 or a 1. So we can see here, this is what the mask is, this is the starting address, and this is the ending address. So when we're setting up those 4 jumpers for the addresses, each one of them has to be either a 1 or a 0 or a don't care. Let's look, for example, at the 6264. The 6264 is masked as 111 don't care. So it's going to respond either to 1110, which is its starting address at E000, or it'll still be enabled all the way up through 1111. So that's how we use the don't care jumper. Now, obviously, this board can hold more memory than the 8085 can address. So another feature that I built into this board is the ability to page memory in and out. And we can see over here, there's 4 LEDs. 3 of these are the address of a particular page. And then the 4th one is just a status LED that you can do whatever you want in the software. So let's look at these page addresses. These top 3 jumpers in each of these is for which page that chip should be selected. So for example, again, on the right-hand side, those are in the don't care position. So that's telling us that this particular chip, this 2732, it is in don't care, don't care, don't care for those 3 pages, for those 3 page address lines. This RAM over here is also has the 3 jumpers installed for don't care. But look at these two 2764s. These look like they are in overlapping memory space here because they both start at C00 and go all the way up to DFs. So that's the same for channel B and channel C. But the difference is, let's look at the page address. 2732's all don't cares. This first 2764 is don't care, and then ending in 0. And this one is don't care, ending in 1. And then the RAM is all don't cares. So what that means is we page these in and out. So we have the page set up. We can either make it so that this guy is enabled or that guy is enabled. And it's possible that if you had, if these weren't exactly overlapping, you could make it so that they were both enabled at the same time. There's no limitation or protection to avoid having pages overlap. That's up to the user, how they want to use that. So to select the page, we have a port selection. This whole board has one command status port, and that port address is set by using this little SIP switch down here. So the way that this is set, these are all 1, and addresses 0, 1, 2, and 3 are set with these bottom 4, so we can see that we have 0, 0, 1, 0. So basically this command status register is configured for port F4. So if we write to port F4, the bottom 4 bits will define the page address that's being active on this board. So for example, to use this, what you do is you will set up the page. So if you want page to be 000, then this chip is going to be enabled because it requires the lower address to be a 0. So this would be enabled at page 2, page 4, page 8. Any of those pages would enable this chip. The next chip would be enabled whenever that least significant bit of the page is set to 1. Since these have the same address, they can't conflict, so we will either set the page address so that that least significant bit is a 0, set that page so the least significant bit is a 1. So the way this board is configured now, this EPROM is always active, and it's always active in that address space from B0 to BFs. This RAM is always active between E0s and all Fs. And then these two EPROMs are paged in and out, with this one being set for a page that ends in a 0, and this one being active in a page that ends in a 1. If we want to switch back and forth between these two EPROMs, we would just send out to port A4 either a 0 or a 1, or any address that ends in a 0 or any address that ends in a 1, and it would toggle between those two EPROMs. All right, well, I have to now go through and test this for a wider variety of combinations of EPROMs, but basically I've tested each of the sockets with each of the types, and I haven't had any problems with this board so far. There is one thing that's a bit of a disappointment the way I set this board up, and that is there's LEDs up here at the top that are access lines, and I was quickly running out of space for any logic glue chips. So I kind of took a shortcut and I connected each of these LEDs to the output of this address equate detector, so that any time that the address matches what it's set up on the jumpers here, those 4 bits of the address matched, the LED would turn on. And that's not gated with the IOM or the read-write signals, because if I gated it with any of those, this would be on for such a short period of time we wouldn't have seen it. So I just said, well, let's just gate it to the 4 portions of the address and the page. And the problem is that it works fine for a smaller device like this 2732, but when you start to get to a device like this RAM, and as you start to have more don't cares for the addresses, when you start to get transient addresses on the bus that haven't been gated with the read-write and the IOM signals, the LED tends to turn on more than it should. So what happens is it works pretty good for this little EPROM. The LED pretty well reflects when we're accessing that, but when we get up to this 6264 that has a don't care in it, now this LED spends a good bit of the time on just as it sees addresses passing through. So I'm going to have to try a little bit harder on the next version to see if I can latch these, keep them on so that they're long enough so that we can see them, but still have them be selective enough so that they only turn on when we're addressing that particular chip. So I'll have to come up with something that I can latch these on for a particular bus cycle. Otherwise, they're just too dim to see them for that short period of the read-write. All right, well, that's, I think, everything about this board that there is to know it's a really fun little board if you want to add a lot of memory to your system. And I'm working on the documentation now, including things like this cheat sheet to show us exactly where the jumpers are and where they go and that kind of thing, and the manual on how to set this up. So hopefully I can finish the testing on this and not come across anything that's wrong in the design, and other than these LEDs that are just annoying. They work, but they just don't work as good as they could have. But other than that, I think everything is looking pretty good on this board. So I just wanted to give you a heads up that this board is going to be available. The files for it are available for download, so you can go off and build your own version of this from the PCB shop. Okay, well, as always, I appreciate you watching. If you have any questions on this board or anything else, let me know, and I will talk with you later. Bye-bye.